1.13, 1.14, modeling functions and applications. We're going to talk about regression models today. And oh my gosh, Robert, so we keep you focused. Here we go.
The idea of modeling, also called regression, is a major component of the AP Pre-Calculus curriculum and will be revisited throughout the course. These topics will utilize the graphing calculators heavily and often include context. In Unit 1, we will work with regression models for polynomial functions, linear, quadratic, cubic, quartic, and for rational functions. Keep going.
Yep.
Building regression models on the graphing calculator. Building a regression model on the graphing requires 2 steps. Entering the data to be modeled. Selecting the regression model.
All right, Caroline and Aiden, that was slightly depressing by Robert, but anyway, we're going to keep going. Oh, so find your stat button. Find your stat button on your calculator. We're going to press it. And then we're going to press in the edit menu. All right. So now you enter in your data into those lists. The X goes with L1, and then the Y value, your outputs go with L2. All right. All right, so step 2, I want you to get into the calc menu. So go to stat, and then go to calc. And so there's 2 linear regression models that you can use. And the first one that we're really going to use a lot because AP Stats is supposed to use this is going to be number 8. It's going to be the linear regression in A plus BX form. All right, so your constant plus your slope and then X form. All right, and so anyway, and now I want to show you how to store something. All right, so when you store something, you're going to use the alpha trace button and select Y1. Here.
Example 1, the age in weeks and weight in kilograms of 5 randomly selected babies from a particular pediatrician's office are listed in the table above. A linear regression y equals a plus bx can be used to model these data, where y is the predicted weight of a baby in kilograms, that is x weeks old.
All right, so we're going to find a model. We're going to find a linear model that represents this set of data. All right, it is these data because it's plural, even though English doesn't make sense to me sometimes. All right, so here we go. So now we're going to select our linear regression. So now you go back to stats. All right, now you go back to stat and then calc and then number 8. So now we're going to store our linear regression as alpha trace, and we're going to type in Y1. And so then we're going to press enter, and we should get this screen right here. All right. Now, my linear regression model is Y equals, what's my A? 3.545, and then plus, what's my B? 0.185, and then X. All right, and so that fits my linear regression model that I just found on my calculator. Pretty good. And so this is going to basically be our predicted value as however many age in weeks my baby is, how heavy they're going to be in kilograms. All right, how much they weigh. All right, so let's go to part B now. Who was my reader? Lucas was my reader. Go.
Using the linear model from part A, what is the predicted weight in kilograms of a baby that is 10 weeks old?
All right, fantastic. So what we're really going to do is this 10 weeks old is my X. This is my time, right? And so I really do just want to substitute in 10 right there, okay? However, I want to show you another trick way to do it. So go back to your main screen. Go back to your main screen, and you're going to get to that Y1 again. Do you guys remember how to get it? Do you guys remember how to get it? Alpha and then trace and then Y1. Now you want it of 10. And so the way that we do of 10, we just don't press 10, but we need to do our parentheses of 10 and then press enter. And so what happened is I ended up getting that right there. All right. And so now I have y of 10 is equal to this 5.395. All right. So this one's not too bad for linear because these both terminated really well. However, sometimes they won't. So I want to teach you this method to be really quick. All right. But really all we're doing is substituting in 10 right here. All right. Cool. All right. Part C.
The weight of the sixth baby is 5.3 kilograms. Using the model from part A, what is the age and weeks of this baby?
All right. So now what does it tell us it is? Now what does it give us? It gives us the weight. And what's it asking for? The h. So the weight is actually the what value? The x or the y? The y. And so we're really trying to set 5.3 equal to this 3.545 plus 0.185x. And then I'm going to try to solve for x. All right? And so an easy way to do it algebraically is to do what? Subtract this over and then divide by 0.185, right? And that could easily solve for it. However, I want to show you another way in case our regression model is much more complicated. All right? So let's go back to our calculator. All right, so my intersection is when x is equal to what? 9.4865, because we're going to round to my nearest 10 thousandths. All right, and so there's another method in case it's more complicated to solve for that. All right, pretty good? All right, cool.
Selecting an appropriate model type. While some problems will indicate which model should be used, you will also be expected to select an appropriate model type based on a given table of values by the context of the problem. Linear models, roughly constant rates of change.
All right, so let's stop there. Do you guys remember doing those like those tables with inputs and outputs? Okay, when did you get a linear model? When was the function linear? When you had your average rates of change being what? Constant. Okay, so these aren't exact rates of change, but they're roughly. Okay, and so that's what the linear means. Keep going.
Quadratic models, roughly linear rates of change.
All right, so let's go there. So again, remember when we did those models, it was the second average rate of change that was constant, and so the first rate of change was what? Linear. Okay, and so that's what just said it again. All right, keep going.
Or roughly symmetric with a single maximum, minimum, or context involving area.
Good. Keep going.
Cubic models, context involving volume.
Be perfect. So, how many units are volume? If I have a unit of volume, it would be what? Cubed. If I have a unit of area, it's what? Squared. If I just have a distance and I'm talking about a rate of change, then it's to a power of 1. All right? And so that's a way to think of it. All right, let's keep moving. Let's put this into practice. All right, pick a reader, Noah.
Jackson. Example 2. For each of the following situations, determine whether a linear, quadratic, or cubic model would be most appropriate. A. Balloons are filled with water in preparation for an epic water balloon battle.
Epic.
Each water balloon is roughly spherical. The radius of each water balloon is measured relative to the amount of water it holds.
Love it. So, is this a linear, quadratic, or cubic? Cubic. Why is it cubic? Because it's volume. All right, it is cubic because it's a representation of volume. All right, keep going.
The Totino's pizzas are on sale for the local grocery store.
You know why? Because they're disgusting. All right.
The price of one pizza varies between $1.99 and $2.19, depending on the variety. The total number of Totino's pizzas are counted relative to the total price of the purchase.
All right, so what's this one? Linear, quadratic, or cubic? Linear. Why is it linear?
Because it stays the same.
It's constant due to the amount of toppings. All right, so my rates of change are constant. All right, part C.
A sprinkler placed in a yard to water the grass. The sprinkler rotates in a circular pattern and waters all the grass between the sprinkler head and the furthest distance it reaches. The radius of the circular path is measured relative to the area watered by the sprinkler.
All right, what's this one going to be? Quadratic. Why is it going to be quadratic?
Because it's dealing with like circles, so it's symmetric.
No, because it's area. All right. All right, example 3 here. All right, pick a reader, Jackson.
The table above provides data for 8 ordered pairs, x and y. Which function type best models the data in the table? linear, quadratic, or cubic? Explain your answer using characteristics from the data in the table.
All right, cool. Is it linear? No, why not?
Because the values don't go up in the same amount.
They don't go up in the same amount. Well, maybe, probably, maybe not. But what's happening? They're going up and then what?
Going down.
Then they're going down. So what goes up and then goes down? A quadratic. There it is. All right, so this is a quadratic. Because why? You kind of basically said it. It goes from what? Increasing to decreasing. It's kind of symmetric. All right, increasing to decreasing. It's symmetric somewhere. Where would it kind of have its vertex? Around 18-ish. We don't know exactly, but ish. It's around 18. All right, that's where it would have its maximum. Would it be a relative or absolute maximum?
Absolute.
Both. It'd be both. All right. And so anyway. All right, part B. So we're going to write an equation of the regression model for this data in the table. So we're going to go back to our calculator, and we're going to go to Stat, and then Edit. All right, so once we get our lists, now we are ready to go and make our equation, our regression model. And so we're going to go back to Stat, and then we're going to go to Calc, and then which one are we going to use? Which one? We want a quadratic this time. So which one's the one that says quadratic? 5. We're going to go to 5. All right. And so now we have our X list is L1, our Y list is L2, and we're going to store our regression. I'm going to store it as something different than Y1 this time. So I'm going to alpha regression, and I'm going to store it as Y2. All right. So I can keep Y1. And then I'm going to calculate. Now we're going to write our equation of our regression model. So now we end up with y equals, and it says my a, x squared. So my a is negative 4.8832 x squared, and then plus 15.9580 x, and then plus 4.9956. And so there is our equation of our regression model that represents that data. All right.
When we use a model to predict values, we expect our model to produce values reasonably close to the actual values, but our models are not expected to result in exact values genuinely. The difference between an actual value and the value predicted by the model is called a residual.
Residual. All right, it's residual. So a residual is calculated by the actual value minus the predicted value. And so when we do our regression models, our regression lines, or our regression quadratics, or regression cubic, that is our predicted value that we use. And our actual value is what it actually is, what's the data actually giving us. So in example 4, we're going to use our model from example 1. So let's go back and look at example 1 real quick. And so what was our equation for example 1? Y equals this 5 point, or no, it wasn't 5 point. It was 3.545 plus 0.185x. And so that was our regression line from example 1. And we're going to find what's the residual of the baby that is 5 weeks old. All right. And so we're going to interpret this after we do this. All right. So what is our actual value of our baby that's 5 weeks old? How heavy is this baby? 4.4. All right. And so our actual value at 5 weeks old is 4.4 kilograms. All right. And so now for our predicted value, we use our regression model. And so all we're going to do is we're going to substitute in what? 5 right here. Okay. And so we can quickly do that with this linear, or we can go back to our y1. All right. We didn't go over it. So we're going to do y1 of. All right. So our predicted value was 4.47. All right. And so how do we find our residual again? We do our what? Our actual value, and then minus our predicted value. So we're going to do 4.4 minus 4.47. And so that's equal to what? Negative 0.0 All right, and so that is our residual. So our residual is negative 0.07. And so let's interpret this data. So what happened with our predicted amount? So our predicted amount was a what? Was it an overestimate or an underestimate? It's an overestimate. So our predicted value was an overestimate.